so the topic in which he presents is we like stuff for people with the value of the Rossa, Udarago, and Pilgrim, my first student. So, well, the Garden of Forking Path is actually a tale by Horgens Borges. And this tale is about a mysterious book wrote by Chinese philosopher Sui Pen. So this book is about this Garden of Forking Path, which is the chaotic novel. In fictional works, each time a man is confronted with several alternatives, he chooses one and eliminates the others. In the fiction of Sui Pen, he chooses simultaneously all of them. He creates, in this way, diverse futures, diverse times which themselves also proliferate and fork. Here, then, is the explanation of the novel's contradiction. Fang, let us say, has a secret. The stranger calls at his door. Fang resolves to kill him. Naturally, there are several possible outcomes. Fang can kill the intruder can kill Fang, they both can escape, and can die, and so forth. In the work of Sui Pen, all possible outcomes occur, each one is the point of departure for other forms. Let me start from an example of a garden of forking path, a very simple one. So we have that stranger knocks at Fang's door. And as we said, there are two possible outcomes. Maybe Fang is killed by the intruder. Let's say we probability speed. Or Fang can kill the intruder. See? 1 and 3. Then at this point, another intruder knocks at the door. So you see, this is a situation which can be iterated and gives rise to a garden of forking path in which there are, unfortunately, infinitely many ways in which the poor farms may actually start to be there. So this is a typical situation that I want to talk to you about, because in this kind of situation, one typically wants to extract some sort of global information about the situation. For example, we'd like to know whether the poor farm has any chance of surviving its very difficult destiny, and whether we can kind of know how long we may expect him to survive on average. Another question we will consider is, okay, imagine Fang will die, but can we understand at which point he's most likely to die? Which stranger, the first, the second, the third, the one that with the high probability will kill him? Well, if we want to understand if Fang can die, well, we have to understand what's the probability that that, right? And of course, we assume there are infinitely many ways in which he might die. Each one has to consider sums up to the actual probability. So, for example, Fang may die like immediately, okay? And this will happen with probability P. Or he may succeed in killing the first stranger by being killed by the second, which gives rise to a path which has probability 1 minus B times P. Or he might be able to kill the first two strangers, now stranger 3 who kills them, which gives rise to a path with another probability. So you see, we have to sum up all this infinitely many paths. This gives rise to this infinite expression, infinite sum here, which in this case we are lucky enough because this is the kind of infinite series that you are like a first undergraduate course in analysis you're able to solve. Yes, unless P is 0, this will sum up to 1. And this gives us, in fact, a way to answer our original question: has Fang any chance of surviving? Well, fortunately, unless P is 0, no. The probability that it dies is actually 1, or whatever the value would be. By a similar reasoning, we all can also come to the conclusion that if we provide an estimation of the expected time survival, which would be I or 1 over P. For example, if P is 1/2, we can expect that he will not survive the first two strangers, actually. We can also see that among the infinitely many situations when he dies, the one which has the most high probability is the person which is killed right away, the less dramatic one. Let us now see a slightly more complex garden of forking path. Now, a stranger knocks at Fang's door, and there are two cases. Either Fang is very quick to kill the stranger, say with probability P, or if he's not quick enough, the stranger will call another stranger. So now Fang finds himself with two intruders to fight with, right? And we can iterate this situation, which gives rise to a garden of forking path, which now is much more complicated because now you see Fang is not quick enough. There are more and more strangers who enter into the picture. Okay, things start to get kind of difficult. in the tale, it says that sometime the paths of this labyrinth converge. For example, you arrive at this house, but one of the possible paths you are my enemy, in another, my friends. You see that here, with respect to the previous case, there are paths which might diverge at some point, but that might converge later, which make things a bit more intricated. So the kind of questions here are, well, let's find any chance of killing all the strangers that appear, okay? And how long is this expected to take? And what can we say will happen in the most likely situation? Well, again, we are asked to understand, to compute the probability that fun will kill all the strangers, right? And again, we have to make a sum over all the infinite in many ways in which we may end up in a situation where there are no stranger left, right? So there is a first situation, fun is very quick. It kills the first stranger and it's done, right? This is probability 1/2. Otherwise, you may, if it's not quick enough, the second stranger shows up, so then he has to be very quick and kill both of them, which gives a situation when he kills the two strangers and probability is 1/8. Or there might be a third stranger involved in the game, and now you see that there are in fact two different stories which diverge and then converge and lead to the situation where, in the end, fun kills of the strangers, right? So we have probabilities 1/5, but we actually multiply this by a coefficient because there are two different paths that follow a similar story. Now you can believe me that if with 4 strangers involved, we have 5 paths, different paths. With 5 strangers involved, we have 7. So it means that we are here trying to compute some infinite series, which starts to be kind of complicated because there are these coefficients here which count how many different paths of a given length exist in this graph. This is a moment where just reasoning like this with standard algebra is not enough anymore. It has to use tools that come from combinatorics. For example, combinatorics, which is the field where people study ways to count infinite families of objects. It is well known that one finds the sequence of numbers, which are called the Catalan numbers, which count, for example, how many, C of n, counts how many binary trees with n leaves exist. And it also counts the number of paths of a given length in this kind of situation, right? So with this Catalan number, we found a way to describe this in series, but still, this does not give us a way to compute the probability. What is this infinite sum? It's very hard to know. Well, as I said, in combinatorics, one often finds himself with a problem of the following kind. You have some infinite sequence of numbers, and you want to compute their infinite sum, but you don't know how. And a very, very strong method is the so-called method of generating function. And the idea is this, roughly. So you have to compute your infinite sum, and you say, instead of computing this sum, I pick a variable from super, which is for each of the elements there into a monomial, you see, with a degree that grows. And you say, by this, have not gained so much in the sense. Our original series now has become a function, which is a sort of power series. Yes, we know that if we have some way to compute this function, then by evaluating it in 1, go back to the original sum. Now, what are we gaining? Are we gaining by this? We're gaining the fact that this function here with something, which is called a generating function, the generating function of the sequence, can be studied with tools from algebra, from complex analysis and stuff. So we may happen to discover properties about the function that will lead us to know what the value of the function, for example, over 1 is. And I will give you an example here of this kind of situation. So let's now consider a sequence which on the pair numbers is just 0, and on the even numbers is 0, and on the odd is the nth Catalan number times this probability here, which is we are really counting the probability associated with the path of length 2n plus 1 in our original graph, right? So we want to consider the generating function that is associated with the sequence is this thing over here. And look at that. If you evaluated this in 1, This gives you back the sum that we want to compute, so the probability that fun will kill all the strangers. Now we don't know how to compute this thing a priori. It's an infinite thing. But there's something that we might be able to guess. So recall that F here is essentially describing the situation that fun is confronted with. So the stranger is not let it stop, right? And we know that there are two possibilities. So with probability 1/2, so fun will get rid of this F, of this stranger, right? But with probability 1/2, fun will be confronted with twice the same problem. So our problem is just twice as hard, right? So we can in fact easily convince ourselves that this function that we cannot compute in principle, but satisfies this equation, which is a factor polynomial equation, an algebraic equation, right? Let's call now y the variable that let's pick a variable y, which will be our function that we want to compute. Then you see that this equation is just giving you like a high school degree 2 equation with y that we can solve just by using the formula from high school. This gives us a way, this is the usual formula to solve degree 2 equations. This gives us a way to write f of zeta without the infinite sum, but just using fraction or square root, right? So we can compute the function. We can compute the function, so we can finally solve our problem. The probability that fun kills a stranger is f of 1, but f of 1, you do the math, to 1. Sure. A bit surprising maybe, but in fact, you can be sure that fun will actually kill strangers.
Sorry. The notation f squared z, it's not that is really wants
It's f of z to the square.
Ah, okay. So
No, it's not the iteration. It's
y
square. Yeah, it should be here.
Yeah, okay, perfect. Thank you.
Thank you. That's good. So we now have a way. We found a way to answer the question. Yes, fun will kill all strangers with probability 1. But to do this, we have to pass through this thing about generating function. And in a similar way, you can also answer the question, how long is this expected to take you? And here the answer is quite surprising. We cannot say that there is a finite expected time. So we know that if we launch this process, it will terminate. We are sure of that. We're almost sure of that. But we cannot say, we don't provide a bound, an expected bound on the termination time. Finally, concerning the most likely situation, the answer is quite similar to the first case situation. The first iteration is really the one which has the high probability, so we don't need to pass through all this combinatorial reasoning. Let's finally get to computer science, programming languages, and in particular probabilistic. Okay, so in fact, this kind of situation, the reason why I'm pointing at these gardens of floating paths, because these kind of combinatorial situations occur quite often when study the termination of discrete probabilistic programs. Let's consider this very simple program, recursive programs. This function, the recursive function that we are defining, takes an input x, and it flips the highest coin. And if it gives head, it will give you x back. Otherwise, it will relaunch the function itself on the input. If you try now to see how the execution of this program goes over 0, for example, when we apply it to 0, you see that it gives rise to a tree which looks very much similar to our first development. Either it gives 0 back immediately, or it relaunches itself. And then either it gives 0 immediately or it launches itself, etc. So if you want to know what's the probability that this program terminates, well, you have to sum the probabilities of all the paths that will go to 0. The situation where the 4th time dies, remember. And we have seen that this is the probability is actually 1. Take the second program, which is very similar. Now our f takes into x, it takes a non-biased coin. It gives hands, it gives the input back. Otherwise, it launches itself again twice. Now you can see that when we apply this program to 0, now it gives rise to your second garden form path. Now you see that the program might start to call itself more and more often, right? So starting the termination behavior of this program is a bit more complicated, but we know how to do it. Because now the probability that f of 0 terminates is given the probability that one will kill all the strangers, which is given by this very complicated sum involving pattern numbers. But we have been wise, so we have found a way using algebra to compute the sum here, and we know that this program will terminate almost surely. This is a bit surprising in a sense. It shows how the problem of understanding if a program terminates surely may be subtle, because this is a program, look at it, which has infinitely many ways of not terminating. If you think there are infinitely many distinct non-terminating paths here. And yet, we are proving that the probability of ending up in one of those paths is zero. So just ignore that. So you see that there is something quite subtle here. So in fact, in the last few years, there's been a rise of attention, the use of this kind of combinatorial method, in particular method of generating function, for studying for programs like probabilistic verification. For example, knowing, estimating the probability that a program terminates, right? Or even for exact inference that have been applied for essentially, what I'm calling here, essentially while programs, and imperative programs that have while loops. If you look at this kind of programs from a more abstract viewpoint, you can the underlying model is that of so-called probabilistic push-down automata. So you know that standard finite automata, you add to them a push-down automata gives you the probability of the possibility of essentially looping, and you have to take the probabilistic version of that. So understanding the probability of termination for this kind of program can be rather subtle. The idea behind all these approaches that you may find in the literature is that you really find a way to, starting from the text of the course, in the course, you write to define inductively this generating function, which is in fact the generating function associated with a sequence of numbers. This number P of n is the probability that the program terminates in n steps. What is nice is that once, if you have ways to capture or to compute these functions, then you're done, because evaluating the function in one gives you the probability of termination. And very nice mark is that evaluating the derivative of this function in one gives you the expected time to termination. So if you are lucky enough to have tools and methods to compute this kind of functions, you can really unveil the probabilistic struct, the global probabilistic. Well, the kind of problems that are financially considered here, of course, the problem of almost short termination, so then the program terminates with probability 1, and of positive almost short termination, which is the problem of knowing whether the expected time to termination of the program is finite. It's well known that if a program is passed, then it is certainly passed. But the converse is not true. For example, we have seen our second example, the one with many strangers, we have seen that the probability of termination is 1, but the expected time to termination was infinite. So the connection between the two probabilities, as we'll see later, is subtle in a sense. But we have also studied, particularly with Davide Barbarossa, we have also focused on a third problem, which is the problem of maximum likelihood estimation. And this is the program then, so suppose you have a program and you execute your probabilistic program and it gives you true. And you know there are infinitely many different ways in which your program might have produced true, and you want to know which one is the one that has the highest probability. So this is a kind of program that is typical, for example, of Bayesian inference or certain learning models. And we want to find a way to compute the executions of the programs within the garden of forking path. We want to extract the path which have the higher probability. What has to be said is that all these programs are difficult, because if you start, for example, if you start from a language which is too incomplete, well, you know that in the deterministic case, termination is quintessential undecidable properties, right? If you are in a probabilistic setting, all these properties are undecidable, but they happen to be even more undecidable than deterministic termination. We'll see later, for example, almost short termination is a I0 to complete property. So it's a very, very difficult property to guess in general. So what's the point of what we wanted to do here? As I said, there is this approach that user-generated function to extract the behavior of this sort of loopy while programs. We wanted to do, well, our question was, can we do something on the lines of that, but by considering functional higher order problems, those that arise from, for example, probabilistic lambda calculus, those that arise from those kind of calculus that we know are related to, for example, to methods from proof theory, Harvard correspondence, all these kind of things. Is there a bridge to make there, right? And to do this, we decided not to start with a language with full power, but to start from a very specific language, which is the language of probabilistic high-order recursion schemes that I will now briefly recall. In fact, this is just a kind of fancy name for what can be called as probabilistic lambda y calculus, just a simple type of the calculus, one that everyone knows, in which we add probabilistic choice, what we call probabilistic, and we have fixed points, the y combinator. Okay, so we add the possibility of making fixed points. Why? Because if we are just simply typing on the calculus, you know that there is strong normalizations at every reduction terminates, which means that the kind of forking path that we can explore will be finite. We will not be really working with the interesting ones with those in which you have infinite many paths, right? So the fixed points gives you this possibility of producing infinite path. So the hierarchical recursion scheme is a way to sort of syntactic sugar for this language here, in which programs are described in a more equational manner. So the idea is that, just to give you an example, instead of just constructing a term with the y combinator and stuff, you just define class as a list functions, which are called non-terminal symbols, as bool-gen, true-gen, for example, by equations which are recursive. So you have a list of equations. Each equation defines by its definition for a given symbol, bool-gen, true-gen, s. And the definition is given by a simplified lambda. Just a simplified lambda. The one on the right is just a simplified lambda term with possibly probabilistic choice. And what is interesting is, of course, that the simplified lambda term will use the symbols, the functions. So this will be, in fact, a recursive definition. The execution. How does it work? How do we compute the system here? So we have to consider there is always one source symbol, this s here. The execution is just, you start from S, each equation, you read each equation from left to right, and you start from S, it will give you to 3-gen, bool-gen of E. Now, 3-gen, you have a definition of 3-gen, so you apply the definition of 3-gen for F, you now bool-gen, and X is E, this gives you this, and then you continue. So you just have to unfold this recursive definition. Okay. As I said, all of this can be put in the shape of just a simplified lambda term with a one y combinator in the beginning. So it's a fixed point, a certain operation.
So why? Just a clarification question. What is the E in the first equation? The E. So the last term in the first equation, S equals 3G.
Sorry, I didn't say this, but E is just a constant symbol. It's a constant of ground time. Yeah. So in the language, yes, we have our constants of ground type, which is in fact, you will see that every computation will actually terminate on this. It's the unique closed form of ground type. You are the constant, so you know that you will just terminate every reduction will terminate on loop. But the output is not very interesting in setting. What is interesting is studying the tree of all the possible computation that you can make. Why are we studying this language, in fact? So there is an important reason that this language has been very, very well studied in the deterministic setting. So as we said, termination in the deterministic setting is a quintessential undecidable property, even in the lambda calculus, it's well known. But in fact, there was this result by Ong that proved that not only termination, but in general, all properties which can be described in monadic second order logic, so a whole bunch of properties, can be checked in a decidable way for all these programs. So these programs, while they have this infinitary behavior, you can in fact check all properties that you can write in monadic second order logic. So in particular, termination is decidable. It's an algorithm that besides terminations for deterministic combination. The other reason is that the probabilistic horse of order 1, which means that it only use function symbol of order 1. So functions over the ground types, more than that. We don't have functions of functions. If you stick there, essentially this model, the probabilistic model corresponds to the probabilistic push-down automata. So the models essentially that you find already in the literature were generating functions that you explored. What is interesting is that if you go beyond order 1, already at order 2, you can see that the problem of almost short termination and of positive almost short termination are undecidable. Which means that this model is actually much more expressive than the kind of computational models that you find in the literature. And so the point is that our target problems are undecidable for this language, so our problem will be to understand what the complexity associated with, for example, solving, answering the almost short termination for a probabilistic horse. And we try to understand how hard it is by studying the generating functions, the complexity of the generating functions associated with the problem. So we try to study the complexity, use tools from combinatorics to study the complexity of the garden of working path that is produced by unfolding this set of highly ordered relations. Let me make you give you a few examples here. So let's take back our first example. So the stranger, the non-fund store, etc. This is describes that by a simple PORs. We have the source symbol and a functional symbol of order 1. Now the source symbol just apply the function to our constant, and the function is defined, well, as we said before, it is x, either it is back x, we put it into p, or it relaunches itself. Either x or f of x. Now the execution will just go as gives f of e, and then you are back with the usual forking path. So from f of b you can either get e, we put it into p, or you can get f of e again, minus p, etc. etc. So you are producing an infinite tree in which you might reach termination, that is e in infinitely many. The second example is quite similar. Now, so you have the same non-terminal symbols. And now the second equation says that I can either give you back x or apply itself twice. And you will get again the tree, the more complex tree that we have seen before when you execute these PORs. But in fact, one can do more complicated examples. So we can go beyond order 1. So the two examples here are order 1. So you see the maximum number or complexity in terms of the types we are considering just is of order 1. We can make, for example, this still rather simple order 2 now probabilistic horse. So we have functions over functions and the function of order 2. And what it does here, so I will just be the identity function essentially, and this L, you take a function and either applies f to x, or it relaunches itself, but now the function f is composed with itself. And you can see that if you iterate this process, what happens is that you will start to have like an exponential growth of the calls to the function f. So the tree will look like something like this, and you see that the call to the identity grow exponentially. In fact, one can see that the generating function, if we will see later, the generating function associated with this program starts to be very complicated because you will start to have exponential terms on the size of the variable, and it's known. I mean, this is a kind of exponential function which is wide beyond what the current methods of combinatorics are capable to treat. So we can easily find ourselves with programs whose behavior is too complex to be handled computationally in a clear way. So now the question that remains is, how do we associate a higher order probabilistic program with loops, with this recursion, to a generating function? This is not obvious. I will give a few hints on how we do that. This is the first point where linear logic, and the picture And in fact, there is a well-known and well-studied semantic, traditional semantics of linear logic, which is called the weighted relational model. And in fact, this is a semantics that interprets programs as families of power series, formal power series. I'll give an idea of how this works. So the semantics is relative to the choice of a continuous ring. Continuous ring is a semi-ring where you can do infinite sums. For example, we take the positive reals extended with infinity, and you will know that all infinite sums will have a value there. You want to be sure to be able to compute, to show that the existence of all infinite sums is there. And you can define it as a category, but I will not enter into the categorical part. The idea is just that you are interpreting types as certain sets of variables, with sigma and y here are just sets of variables. And the morphism, so our program, will just be, so our program from sigma to y will be a family indexed by y of power series in the variable sigma. The power series with coefficients in Q, so Q is the ring where, the semi-ring where we take coefficients. The variables are sigma, and you take y many of these power series. For example, the Booleans will be just a set with two variables. The natural number will be a set with omega variables. And if you have, for example, a term which goes from bool to nut, you will have not many, so omega, so an enumeration of power series, t, in two variables. Because bool just means two variables. So the types are just sets of variables, which can be infinite general. And programs are power series in these variables. We'll see an example in a moment. What is important is now that there is a sort of very direct translation. So we said a probabilistic course is just a set of equational definitions, right? Of recursive definitions. Now the idea is that every non-terminal symbol of the type associated with a certain number of variables. So every non-terminal symbol is a set of variables. And its equation defines an equation, provides the equation that defines the determinant symbol is associated now with an equation defining the associated variable with respect to all the other variables. For example, in this the situation that we have, one of the situations we explored is the one where we take as a coefficient ring power series in one parameter zeta. Zeta is a parameter that counts essentially the reduction steps. And now, from the equation definition of the original terminal, we obtain an equation of definition of the variable. In particular, you know that among all the variables, there will be one that corresponds to the source symbol. Now, the interpretation of the mode of the program will be the minimal solution of this system of equations. So the force, the probabilistic force, becomes a system of algebraic equations, essentially, right? With variables, and the interpretation of the program is the minimal solution of this system of recursive equations. In particular, if you have each of these, so this minimal solution will be a list of generating functions in the parameter zeta. And in particular, there will be one which is associated with the source symbol, step S, which is really the generating functions that we're looking for. Because when we apply this to one, this will give us the probability of combination. And when we apply evaluate its derivative, one, it will give us the expected time to combination. Let's see an example of this. Again, on our starting examples here. So this is the probabilistic horse that corresponds to our first Gaussian fortune path. Now we said each equation translates into equations for variables. So the first equation just says essentially, since the constant E is just something that terminates with probability 1, this just says that the two variables, the variable associated with S and the one associated with F are the same. And the second one says that the variable associated with F does nothing with probability P. But I put a zeta because I'm saying this gives nothing, but there is a computation step to base. The zeta means I'm doing one computation step, or with probability 1 minus P, it gives itself back. It's again error of F. And now the generating function that corresponds to this program is just the minimal solution to this system of equations. In this case, it can be computed by easily, but in fact, it corresponds to what we were computing by hand before. In fact, it gives this generating function here, this power series, which is in fact can be simplified into a fraction of two polynomials, essentially, what is called a rational power series. And you see that if we evaluate this in one, so theta becomes one, you see that this gives one. So the evaluation of this power series one is the probability of termination, which is in fact one. So the model is translating a system of equations over lambda terms into a system of equations over variables, and the minimal solution of that is a power series that gives you the probability of termination. Let's take a second example. So you remember the probability course is similar. And now, what is interesting is now the second equation, the variable is equated to itself squared here. It's the only difference, okay? So you have an algebraic equation of this form, which defines the variable of the non-terminal f. Now the solution is the one that we were looking at before, the one that uses the Catalan numbers, the one for which we found you have like a simpler expression of that. Again, if we evaluate this in one, gives us one, the probability of termination will be fact. Okay, so this gives us a way to just transform each probabilistic force into a system of equations. Yet this does not give us a way to solve the most short termination problem, which, as we know, is undecidable. It's very badly undecidable, right? So in the example I showed you, everything works because everything is fine, essentially. But in general, the system of recursive equations that you extract from the program will be infinite. You will have infinitely many variables, and this phi here might itself be a power series, something which is way beyond any kind of computational method that you might apply to go. So, as I said, our goal was that of studying the complexity, the difficulty of the forking part of the program by studying the complexity of the corresponding generating functions. Now, in the field of combinatorics, there exists several known hierarchies of generating functions with respect to how difficult it is to manipulate them and to compute them. And the typical hierarchy you find is the one that has rational generating function, algebraic, polynomial, and then the whole class. Let me recall a moment what the rational and algebraic generated functions means, what they are. So, as we said before, function is rational when written as a fraction of polynomials. Now, this is a class of generating functions which is very, very studied, and it corresponds to the example that we saw before, the actual at first garden 14 path. And what is interesting is that typically this kind of generating functions can be defined using a linear system of linear recursive equations. And there exists a very efficient method to given like a system of linear recursive equations to compute the closed form, so compute the two polynomials, P and Q, effectively. And once you have those, you're done, because to evaluate your function, you just have to compute the polynomials. It's something that you can do very efficiently. So this is the class for which you have the strongest methods. You can really compute exact values for those. A wider class for which we might have less information is the one of algebraic series, which are those for which we might not know how to write them explicitly, but we know of some polynomial equation that satisfy. So the fundamental information here that we have is that we don't know how to compute f, but we know that it's the roots of some polynomial. Even the example here is the one that we saw with the Catalan number, but this is an example where we were able to find close to which compute this. This is not necessarily the case, but still here, just from this equation here, there exists efficient methods to approximate functions, to approximate the function to a degree, but also to solve some specific problems. For example, the problem to know whether the function evaluated in one is one, which is the one that we are interested in, can be formulated, in the Tarski first order theory field. Everything is now algebraic. So we are looking at a solution of some algebraic equation. So we can write a formula of first order logic for the reals, and then since this series is decidable, we can check it. So even if we don't know how to do that in general, we can check if its value on one is actually one. So we can hopefully check a more short termination. So the whole point is now how can we ensure or check if our probabilistic higher order recursive scheme yields a generative function that we can manage to make rational or algebraic. This is the second point where we take the toolbox of linear logic again, because the idea was, can we find some refined type system with respect to this starting from a simply type of calculus, looking for some refinements of the simply type of calculus that would ensure us that if a probabilistic works is typable in our refined system, then the generating function is algebraic. And so we can apply all the methods that people in combinatorics know very well to answer all other questions, right? So the fundamental idea here is to use the theory of bounded exponentials. So in linear logic, there is a well-studied theory which uses function types of this form here. And the function type of that form here is essentially a type of function that may take an input of type sigma and produce an output of type tau by using the input at most gateways. So there is a restriction on the number of times that you may copy your input, which is provided by k, which is typically a natural number. So the idea is that, since we said before, a type is in our word, in our semantics, is a set of variables. The fact of bounding the number of times that you can use type magically gives rise to types that correspond to finite sets of variables. So you can interpret with higher order types with a finite number of types. So this is not even too many people, but the key idea that magically ensures that our infinite recursive systems here become in fact finite systems, so in fact algebraic systems in general. So we define this class, this work with Alago and Guido Fiorino that we are presenting next week at Mix. The class of bounded probabilistic horse, which are the probabilistic horse which are typable in our refined system. And this refined system ensures the fact that when you interpret the program is in fact described by a finite number of polynomial equations, recursive polynomial equations. So to find the generating functions, you have to solve a finite number of polynomial equations, which implies in particular that the minimal solution, so the generating function, is algebraic. So we can in fact use all things which are there. So in particular, the type system is strong enough so that all the probabilistic horse of order 1, those which will already be treated in other ways without using other calculus, are typable in the system, so are part of this thing. And in general, or at any order, the problem of past and past become decidable. If the probabilistic horse is type there, because we said there, once the generating function is algebraic, we can check if its evaluation in 1 is 1. And we can check the same thing, similar stuff for its derivative, because the derivative will be algebraic itself. So this gives us, beyond the solution to this problem, it gives us also methods to do approximated inference. For example, to know whether if the probability of termination is not 1, then we can know if it is something around 95%. And you don't get the exact value, but we can say if we are close enough to 95%, those kind of things. And it gives us asymptotic formulas, ways to understand how fast the probability of termination decreases when we consider derivations which are longer and longer in general. A little spin-off of this work is that I suitably define this type of system, always with ideas from linear logic. We can obtain an even much more restrictive system which ensures now rationality, not just algebraicity. And the idea is that you are forcing the recursive system of equations that you obtain to be a linear one which is like an affine linear system of equations, which can be written in this form. So this is the kind, as I said before, of systems from which we can compute a closed form efficiently. And this gives a class of probabilistic hordes which is more restricted, but from which we can extract much more information, which includes, for example, our first example. So, for example, the closed form for the derivative function can be computed in random time. The past and past can be solved in random time here. And we can also have exact inference method. Now we can really compute exactly the probability of determination, which will be a rational number. So we can say the probability of determination is really 95%, not more or less 95%. Just to give a hint of how graded exponentials, so bounded exponential, enter into the picture. Well, the system is, as I said, you start from simple types and you replace the usual arrow with this bounded arrow. But in fact, there are two kinds of types. There are a class of types that are called finite array, which are those in which the bound is always a natural number. And there are types called infinite array, where you can, in fact, admit an infinite bound. You can use your input in incremental. So you don't need to impose finiteness everywhere. Okay? The goal is always to have that any type, so every type that appears in a type derivation corresponds in the end to a finite set of variables. So the system is something like this. It's a bit involved, so I'm not giving the details. Essentially, you have three environments for variables, but this is because the probabilistic, of course, have different kinds of variables. We have the blue ones are in the context where you're typing the non-terminal symbols, for example, the source. This is given by a specific environment which is used non-linear, like in the use of specific element output, which means that non-terminal can be used as many times as you want. We have to pay to use it. And similarly, there is a context in Weizsäcker for the parameters like the zeta, or you can have some sort of variables that you're used to you're admitted to use anyway, without any kind of bounds. The crucial point is the orange one, which is the environment where you type the variables, the standard variables that use by term, or those that appear in the recursive definition of probabilistic course. Those have to be graded, which means that the type assignments have a finite grade. We have to say this variable, I will use it no more than k times. And this is the crucial restriction that we have to impose in order to attain that the interpretation of the type derivation will be whatever, by in fact, a family of power series in finitely many variables, which is the thing which ensures all the results that we have. Well, rationality just amounts, in fact, that requiring a drop in the nonlinearity in the blue environment, very simple, which means that non-terminal now can only be used at most once. This is the simple switch. So, okay, let's see an example. This was our first example here, and no, this was the second example here. So, as I said, the point is that we want to, so each non-terminal is defined by a lambda term. So we want to type the lambda term in the simple guide of the calculus. This is what usually one does, right? And now we want to type it in our system. So, for example, here, so the non-terminal f corresponds to the function here, which is the function defined by this term. Okay? The crucial point is that now we want to type this function, which uses, of course, the non-terminal f. Right? And here we can do it, it's no problem. The crucial condition which ensures that the term, the probabilistic course is bounded, is now the fact that, see, you will have a type which is associated in the environment with the function symbol, and the type which is the type that you are able to derive for the term that describes the function symbol. And you want these two to be the same. You want to be able to associate the function symbol and the definition of the function symbol, type them with the same type. If you can do this, then the probability, of course, is in fact bounded, so it's correct for a criterion, and in fact, this would imply that the derivative function is satisfied. I can show you like a counterexample here, which was the one that's essentially the one that we saw before, the one where we have a second order thing which can compose its argument itself. In fact, the corresponding derivative function is not algebraic. It can be seen that it's transcendent, so it's not algebraic. And in fact, if we try to type the term that corresponds to the definition of L, so down tau, it will be just O or O. So we're supposed to start with a given K, with a given finite index here, a given bound here. And in fact, the system of linear logic will force 2k. So you cannot manage to obtain the same time to the left and to the right. So if this is a function that uses its input k by assumption, you obtain in this way a function that will use its input 5, basically because it's a computing function. So in fact here the fixed point condition fails for good reasons, because this is really kind of support that we want to avoid because we don't know how to treat them. Okay, they are too difficult. Okay, I want to talk about the most likely execution path because this is the beginning of a completely different story. I will just give you the final picture of where we are so far. So, as I said, I'm not talking about we deal with the third part. So if you start from a Turing complete language, for example, probabilistic PCF, as we said, IST and PIST are undecidable. They are much worse than undecidable. They are pi02 and sigma02 respectively. Complete, actually, but we start with this. And even most likely, maximum likely estimation is pi01. If you take the probabilistic horse, what we know is that these problems are undecidable and in fact pi01 hard. Now, what we have seen is that if now we restrict the probabilistic horse that using our methods and algebraic generating functions, then the problems become decidable. In fact, decidable in exponential time because you basically have to use the decision algorithm for the existential theory of the reals to solve them. While if you are in the system that ensures that generating functions is rational, then everyone becomes polynomial time because you can find the formula to compute the generating function. There are partial polynomials, you can find those polynomials, and we can solve, we can answer kind of everything. So this is essentially where we are. Where do we want to go? There are many directions at the moment. So one thing we're looking at, particularly Guido is looking at now, is whether we can go beyond just termination. We would like to explore, for example, answer questions concerning the probability that a certain formula of monadic the logic is true. Of course, for example, an idea formula that says that certain non-terminal symbols may occur infinitely many times during the execution. We want to know what's the probability that a certain symbol will occur infinitely often in this kind of things. Because with this kind of problems have a solution and methods in the deterministic case. So the question is, if we restrict to the algebraic rational situation, can we answer some probabilistic question? And we want the natural thing is to go beyond algebraicity. As I said before, there are hierarchies that go beyond algebraic derivations. And so we'd like to use other tools and see if there are tools and methods from notorious to view beyond algebraic function. And finally, the big question, which is in fact the question that motivated for the start of all this thing, that we were, as I said before, in the deterministic setting, we know that termination, for example, PCF, is a decidable property, the Turing complete language, but it becomes decidable if you take the deterministic higher order recursion scheme. This was the cornerstone result Now, if you go to the probabilistic setting, we see that almost sure termination becomes pi02 for PCF, it's really complex, but you would expect that for the probabilistic horse, its actual logical complexity would be smaller. So you would expect, since it cannot be better than pi01, but would be actual algorithm. Can we see that and past our conjectures that the problem of almost sure and positive almost sure combinations are actually pi01 in the case of the old probabilistic horse. This will be interesting because it will give algorithms to approximate probability of termination for an arbitrary probabilistic horse, but we are very far yet from this from answering this question. But it was really our fundamental original motivation. Okay, let me stop here. Thank you.